Okay, so the plan for today is to finish up the last couple topics in 3.1 and then start on 3.2, measures of variation, continuing this chapter 3 perspective of descriptive statistics. So we're looking at numerical measures that we can use for describing data sets. The quote of the day today from Horace, the Greek, or not Greek, Roman lyric poet, in his satires. I think it's applicable because of the use of mean or mode in a sense. There is a mean in all things, too far to the right or left of which good cannot be found. So maybe with the kind of seeming extremism that we're seeing leading up to the elections and seemingly every battle, and also our discussions of means and modes and so on, maybe an applicable quote for today. So speaking of measures of center, we talked about mean, median, and mid-range last time. We talked about how to compute them both by hand and on Excel. And I want to just really quickly run through that again because we're going to be looking at how these three measures of center kind of relate to skewness, to skewness and outliers. Okay, so just a really quick recap. We talked at some length about these three measures last time, so I'm not going to spend a ton of time on them, but just to recall, for the mean, we said for a sample, we denoted X bar. And if we have a data set X1, X2 through Xn, we add up all of the data points values and divide by the sample size n. So that was our mean, that was our average. We could also denote this by the Greek letter mu if we were talking about a population. The median most often we just call MD, and it's the middle number. And by that I mean the data value associated with the data point that is the middle data point after we've ordered our data. So by this I mean take x1 less than or equal to x2 less than or equal to all the way up to xn, and take a data point in here that's going to look something along the lines of x subscript n over 2, like half the size of the data. It's, you have to, it depends slightly on whether whether n is even or odd. We might have to add one or subtract one here or there or something, but it's more or less like, let's say x sub n over 2. And this data value is the median. And we said the way that we kind of, practically speaking, got to the median, if we had a list of data that were in order, we just kind of cross off one lowest and one highest, cross off the next lowest and next highest until we get down to the point where we either have one left and that's our median, or if we have two left, we just average those two. And then the mid-range was like the average of the extreme. So while the median is kind of like the average of the middle numbers, and if there's just one middle number, it's just that number, the mid-range is like the average of the extremes. So the mid-range is x min plus x max over 2, the minimum data value plus the maximum data value over 2. Or if we have ordered our data like this, it's going to be x1 plus xn over 2, but that 1 and n only applies if we've already ordered our data. Oh, let me close my email, or we'll keep dinging the whole time. There we go. So that was our, our mean, median, and mid-range. My throat wasn't this scratchy until I started talking, I guess. It's making it a little worse, but it's fine. Okay. So now let's think quickly about how these measures of center might relate to skewedness. We discussed skewedness briefly in chapter 2, and we said that if we have a histogram that has outliers on one side, so like a graph like this, for instance, there is the potential to get some data values that are way off to the right. Here's where most of our data is. We can get some values that are way off to the right, but we don't see similar extreme values off to the left. We would say this is some evidence of right skewedness. That it seems that we're able to get outliers, that there exists some outliers in this population, and that they tend to be towards one side of the spectrum. We could also have left skewedness. Situation like this where we have some outliers to the left. Again, what do we mean by outliers? At what point is a graph skewed versus not skewed? This is all pretty subjective at this point, right? But an outlier is kind of like a data point that doesn't fit in with the majority of the data set. Again, very subjective definition at this point, but um, for extreme examples, we can probably comfortably say, yes, that's an outlier. For gray area examples, I don't know. Some people might call it an outlier, some might not. So still a little bit subjective. This would be left skewed because the outliers are to the left of where most of the data is. Now, just as a side note, keep in mind that if we had a situation where we had outliers on both sides, that can certainly happen. Well, we have outliers here, but they're kind of distributed on both sides, kind of roughly evenly. This would not be skewed. This would still be symmetric. Symmetric, in other words, not skewed. Uh, so just because we have outliers in a data set doesn't immediately mean that the data set exhibits skewedness. It's if we have outliers and they tend to fall to one direction over the other preferentially. However, we can say that if our data set is skewed, if we're saying there's evidence of skewedness, then that means there have to be outliers, right? So be a little careful with the logic there. Just because there are outliers doesn't necessarily imply skewedness. But if we say that a data set is skewed, then that implies there have to be outliers because skewedness indicates the presence of outliers on one side. Okay. So let's try to dig a little bit deeper into skewedness and come up with a test that's at least a little less subjective, a little more objective than just looking at the picture and saying, do we think that this picture looks like a left skewed or right skewed picture, this histogram or line chart or whatever graphical technique we might use from chapter 2. So one question I'm going to ask myself is, let's just suppose I had a data set where all my data were nice, normal data. They were all nice, typical data, except one outlier. Let's say that I had a data set like this, where I have a bunch of, bunch of like reasonable data over here. I can't like seem to draw today. I think I have my trackpad at a funny angle or something. And then we have like one huge outlier over here. So if I think about this data set, how would that one outlier affect my three measures of center, the mean, the median, and the mode? Or maybe another way that I could think of it is, what if I thought of this outlier kind of starting like grouped in with the data and then moving all the way out here. How would that movement affect the mean, the median, or the mode? Well, if I think whenever my outlier was kind of not yet an outlier, if I think of the median would be here, right? If I think of the computation of that median, what I would do is I would start by taking my lowest data value, something down here in this stack, my highest data value, and immediately canceling them. And then I would keep chipping away until I get, something that's like in the middle of this stack or whatever. But I immediately canceled this high data value. If it gets a whole bunch more higher, it just gets immediately canceled still. My median actually doesn't care at all about outliers. So my median is unaffected. Since I'm like basically chopping off the top almost 50% of my data and the bottom almost 50% of my data and just looking at the middle, I mean, for the median to be affected, if we were going to say that the median was affected by an outlier, we'd have to have like half of our data being outliers. And if half of your data is outliers, I mean, it's kind of hard to call them outliers then, right? You probably have something like a bimodal distribution instead. So my median is unaffected by outliers. And therefore it's unaffected by skewedness. If I have a graph that exhibits skewedness one way or the other, those outliers aren't going to affect the median. My mid-range, on the other hand, it only looks at those extreme values. Where the median immediately chops off the extreme values and ignores them, the mid-range only looks at the extreme values. So if the mid-range is looking at these two numbers and taking their average, maybe somewhere right here in the middle, and then I take that rightmost data value and push it way further off to the right, now the mid-range is looking at these two data values, right? The mid-range has increased substantially. The mid-range only looks at the two extreme data values. So when we move a relatively high data value to be a big outlier, that's going to affect the mid-range an enormous amount. So the mid-range is affected significantly by outliers. Now, if we think about the mid-range versus the mean, the mid-range is x1 plus xn over 2. If I kind of forgot about all of these middle numbers here, x2 through xn minus 1, and I look at the mean, it's kind of, if I forget about those middle numbers, it looks a little bit like the mid-range, x1 plus xn in the numerator, except instead of dividing by 2, I'm dividing it by n, right? So the mean still does like inspect those extreme values, but the weight that each of those extreme values gets, instead of being like 1/2 of the contribution, it's like 1 over n of the contribution. If n is 100, x1 and xn only play a 1% role in determining the mean, and x2 through x99 each also play a 1% role. If n is 100, the biggest and smallest values each play 1/2, a 50% role in determining the mid-range. So the effect of outliers of x1 or xn, xmin or xmax, gets diluted in the mean. It gets divided by a larger value n, a larger sample size, where in the mid-range it's always divided by 2, no matter how big the sample is. So the mean is going to be affected by outliers. We still have an xn in there. If that number gets much larger, the mean is going to get larger, but it's only going to get larger at like a factor of 1 over n of how much that one data point got larger, where the mid-range gets larger at a rate of like a factor of 1/2 of how much larger that outlier got. So the mean is kind of in the middle. So the median is essentially unaffected by outliers. It's, as we might say, robust to outliers, robust to the presence of outliers. The mean is somewhat affected, and the mid-range is substantially affected or significantly affected. So what does this mean? This means if, or let's do right skewed because that's where I started. So if our data set is right skewed, then we would expect to see that, well, that presence of outliers on the right that is not counterbalanced by outliers on the left. That's what it means to be right skewed. I'd expect my mid-range to be quite large, to be quite a bit bigger than the mean, because it's being pulled way out to the right by this outlier. And I'd expect the mean to be a bit larger than the median. The mid-range gets affected the most by outliers, the mean the next most, and the median is kind of like an anchor. So in the presence of some right outliers not balanced by left outliers, the mid-range should get pulled way off to the right, the mean a bit off to the right, and the median should stay put. And we should be able to say the opposite as well. If we're left skewed, if we had outliers on the left instead, I would expect my mid-range to get pulled way to the left and be much, much less than the mean. And the mean should be less than the median. Now, when I put two inequality arrows, like greater than, or less than, that just means a lot bigger than or a lot less than. So not just by some tiny margin. Now, we have a bit more of an objective way to look at skewedness. We can say, okay, if we're skewed one direction or the other, our measure of center should line up this way. We still have a little bit of subjectivity, because what does it mean to be a lot greater than or a lot less than? Still kind of subjective, right? But probably a little more objective than just looking at the picture and saying, does this look like a right or left skewed distribution? So one thing that we do in statistics quite a lot that is quite different than most math courses is we use kind of less precise logic. We use ideas like evidence in favor of or evidence against, rather than precise A implies B type logic that you would see in, say, algebra or calculus or trigonometry or something like that. So we have a statement here. We have if A, then B. This is like if A, then B. Or we might say A implies B. Now, as a general rule, if I have a theorem, if A, then B, if A is true, then B is true, it doesn't go the other way. If I prove a theorem, if A, then B, or A implies B, that does not prove B implies A. That does not prove if B, then A. But kind of from an evidence-based standpoint, if you say if A happens, then B has to happen, if I see the B has happened, that gives me a little bit more confidence that A may have happened than I had before I observed B. Because if I saw that B didn't happen, then I know that A could not have happened, because if A happens, B has to happen. So if I observe B, that's evidence in favor of A. It's not a flipping of the propositional logic. that we're trying to do here, we're speaking statistically. We're speaking in terms of evidence for, evidence against. So we can make the following claim on the basis of this. This is everything I've done up to here is basically, hard math. But what we're doing next is a little bit soft. It's a little bit in the kind of statistical sense, like we have some evidence in favor of something. So I have an if A then B, that's a precise logical statement. But I could flip it around and say if I see B, then I have some evidence in favor of A. In other words, if the mid-range is much larger than the mean, which is much larger than the median, then there's some evidence of right skewedness. So if I said, if this ordering of the measure center was true, then there is definitely right skewedness. That would probably be a step too far. That would be most likely misusing the logic above, or I would at least have to supply some extra argument as to why I should be allowed to reverse that that implication. That's not what I'm saying here, though. I'm kind of, some people might say giving myself a cop out, but I'm being careful with exactly what I'm saying. I'm saying there's evidence of right skewedness. I have kind of one more piece of evidence that favors right skewedness, but it's not conclusive. That's one of maybe the frustrating things for some people about statistics is that we almost never say like, you know, this thing is certainly true. We say, there's evidence in favor of this being true, or we say something very complicated like, given that the p-value is less than 5%, we consider this to be statistically significant. It's like, so we tend to say things that people don't understand and then they misinterpret them, but we're saying that there's evidence of right skewedness when our measures of center align this way, when the mid-range is much bigger than the mean, which is much bigger than the median. And vice versa, if the mid-range is much less than the mean, which is much less than the median, there's evidence of left skewedness. So our first test for skewedness in a sense was look at the picture and see if it kind of looks like one of these. Very subjective, very hard to even for the same person to be consistent from picture to picture, let alone to get consistency across different people. We know something that's at least a little more objective. We can look at three numbers and we can certainly tell whether they even line up this way, right? If the mean was less than the mid-range, or if let's say the mean was greater than the mid-range, which was greater than the median, they don't even line up the right way. So we can kind of pretty comfortably throw out skewedness at that point. If the mid-range is a bit bigger than the mean, which is a bit bigger than the median, well, might somebody else call that substantially bigger? And you called it just a little bit bigger, or vice versa? Maybe. So there's still a little subjectivity here. What does it mean for one of these measures to be substantially bigger than the other? But at least we're a little bit more objective. We have a slightly more objective test. And then we'll see in the next section, we'll have a completely objective test that we can apply. And it's kind of based off of this idea. Okay, so any questions on these three measures before we move on? Okay, I would like to go back into our chapter 3 demo. So I posted that in the chat earlier. And as I mentioned earlier, I fixed the issue with the salary data. So now you see that these 6 cells don't align to salary anymore. So let's rename them. So we have our Ashley data that we didn't name. We have our Brandon data that was named Brandon already. And then let's select our salary data and name it salary. As an aside, if you ever need to change these names, you can go over to formulas and this define names and name manager, you can change them in there. But since it was our first time working with Excel last time, I didn't want to go through all of that. So it's not super hard to change these names. I just, I'm not sure why it had salary linked to these 6 cells instead of the 7 here. And just to quickly recall, for the mean, for Ashley's mean, we can do say equals average and select the cells of interest. For Brandon, equals average, and we can start typing out Brandon, and we see it comes up with a suggestion. We can hit tab to accept the suggestion, end the parentheses and hit enter. And for salary, same thing. So equals average, we can hit tab to select that first function there, average. And if we start typing in salary, we see that salary comes up as a suggestion. Hit tab to accept that suggestion. That looks like the right data set now. So there's our mean for each of those. To do median, and again, we did this last time, so that's why I'm going through this pretty quickly. So if you weren't in class last time, take a look at the recording. We went through it in more detail. But the median for the Ashley data, median for the Brandon data, and the median for the salary data. And the mid-range, remember that we had, we don't have a built-in function for mid-range, so we had to use the max and min functions. So I want a parentheses to cordon off the numerator. And then I need to use the function minimum. I need another open parentheses and a closed for the cells I'm inputting into the minimum function. So min of B2 to B6, end parentheses, that's one piece. To that, I want to add max of B2 to B6. That's a second piece that's in the numerator. I still have my open parentheses for the numerator, so I close it. That finishes out the whole numerator, and I divide by 2. And we see Ashley's mid-range is 8. If we look at Brandon, his mid-range, again, I open a parentheses to cordon off the numerator. So equals min of Brandon. That min of Brandon is one thing, plus max of Brandon. That's another piece, another term in the numerator. I want to close off my numerator and divide by 2. And then I can do the same thing for salary. Min of salary plus max of salary over 2. And if I look at these, so median I think of as being like my anchor. It's the thing that doesn't get affected by outliers. If I take a look at these and inspect them to see if I think there might be outliers, or there might be skewedness, maybe I should say. Well, actually, these 3 measures of center, the mid-range, the mean, and the median, are actually all exactly the same. They're all exactly 8. Her data set seems to not exhibit really any skewedness at all. Maybe we would say this even represents evidence of symmetry of her data. Brandon, his mean is 7. Or sorry, his median is 7. Mean is 8. Mid-range is 8.5. So the mid-range is a bit bigger than the mean. The mean is a bit bigger than the median, but it's only like a half or 1 point on a scale of like 7 or 8. So like 15% difference between each measure, they do line up the right way. But 15% difference going from one to the next, I probably wouldn't call that substantial enough to convince me that there's some right skewedness going on here. If anything, there would be right skewedness because the mid-range is bigger than the mean and the mean is bigger than the median, but probably not substantial enough. But somebody else might come to a different conclusion. They might say they think it is evidence of right skewedness because maybe they do think a 15% jump between each of them is big enough for them to be convinced. So again, a little bit of subjectivity here still. And if we look at the salary data, again, the median is kind of the anchor. The mean going from 28 to 42, about a 50% jump. And then going up to the mid-range, 42 to 62, again, 20 units on a scale of 40, or again, about a 50% jump. These do line up the right way. The mid-range is bigger than the mean, and the mean is bigger than the median. They do line up the right way that it could represent right skewedness. And in this case, looking at a 50% jump for each of them, I probably would be pretty confident saying that this is right skewed. That also does seem to be the case looking at the data set. With only 7 data points, we can just explicitly look at the data set and see what we think about it. And it does seem like most of the data is clustered around the 25 to 30 ballpark. There's one up here at 55 and then one at 100. That 100 sure kind of like feels like a right outlier. And I don't see any left outliers that would kind of counterbalance it. There's nobody down here at 0 or negative 20 or something like that. So this kind of feels like it ought to be right skewed just looking at the data, and the measures of center kind of line up that way as well. So again, still a little bit subjective. Maybe I wouldn't call Brandon's data. I wouldn't make the call that there is evidence of right skewedness here, but maybe somebody else would looking at the same data. They might have a different interpretation. They might have a different cutoff for making that call. But I think most people would make the call for the salary data. And of course, we ought not make the call for the Ashley data because it's the numbers don't line up this way at all. So I think Ashley and salary are probably pretty clear. Well, Ashley is definitely clear. Salary probably pretty clear. Brandon, maybe a bit of a gray area. Okay, any questions so far? Just give me 1 second here. All right. So let's, if there aren't any questions, I don't see anything in chat. Let's jump down to the next measure of center, the mode. So the mode is kind of a strange measure of center. It has some plus sides and some kind of big downsides. Let's kind of take an optimist approach to start with here. Let's look at an area where the mode is really great. It really comes in to save the day. Let's say that I'm the fashion designer. I'm sitting on the street corner trying to decide what's the cool the cool colors this year that I want to, print my designs in. And I make some shirt color observations. I have some reds, greens, yellows, and blues, and um, we'll just say that these are the only 4 colors that exist. I think for like 80% of men, these are the only 4 colors we know. So we don't know what fuchsia or lavender or any of those are. So we'll just say these are our colors. We ticked off 5 people with red shirts, 1 with a green shirt, 2 yellows, and 2 blues. Now let's say I want to measure of center for this. I want to know what's the typical data point look like. So I might be tempted to just jump back and say, okay, I compute an average or get a median or right. These are pretty typical things, but the problem is if I want to compute an average, or a mid-range, I need to be able to add data values together. I can't really add red, green, yellow, blue to each other in any meaningful way, at least not in this context. Maybe if I was a physicist working with lasers and thinking of these colors as having certain wavelengths or something, maybe a different context, maybe we could make some kind of argument, but certainly not in this context. I think it would be a heck of a stretch to make any kind of argument like that where we could even start imagining a way to add these together. Okay, what about the median? I mean, the median doesn't require us to add things together. We just have to pick a middle number or a middle value. But even here, there's not a natural ordering or ranking, right? I mean, again, I don't think we would really want to think in terms of wavelengths or and color intensity, anything like that. I think that's probably um, not inherently linked to the thing we're interested in, which is colors that people are preferring. I don't know, maybe some psychologist somewhere figured out that people like red over blue because of the wavelengths or something, but I think, again, that would be a pretty big stretch. So really, this is just qualitative or kind of categorical data. So I can't even really impose a natural ordering or ranking on it. So how can I talk about what's the typical data point? Well, pretty much all that I can do here is count the number that are in the bin, right? I want to use numbers somehow. I want to use the structure the numbers have, ordering and being able to add and so on. But my actual data values don't have any of that structure to them. But once I start tossing those data values into different bins and I start counting the number that are in each bin, my frequencies actually are like real numbers. They do have that structure to them. So my frequencies themselves actually in some kind of meta sense represent like ratio data related to this set. So I can look at these frequencies that are always going to be numerical, even when I'm looking at qualitative data. These frequencies will be numerical. They will have, at the very least, the natural ordering. And I can pick out the highest frequency. In this case, that would be 5. And then I can look up what is the data value associated with that highest frequency. I can essentially always do this, right? So I can say, what's the most frequently occurring data value? So again, what do? I look at the frequencies. I find the highest frequency. Now, importantly, 5 is not my mode. 5 is the thing that kind of points to my mode. So my mode is red. The mode is the data value that has the highest frequency. Another place where the mode is really nice is when we start developing these the kind of background of probability theory in chapters 4 and 5, and we get to chapter 6 and we have continuous distributions. Things like finding a maximum is actually a really well-defined problem. If I have a nice smooth function, finding a maximum, I can figure out that, okay, this is the maximizer. In other words, it's the input that yields the highest output. The way that kind of, if you think of this is like a function where you input the bin that you're interested in, and the output that you get is the frequency. So the input of red yields an output of 5, or the input of this value on this axis yields an output that's this height. I can actually find the input that yields the highest output pretty easily, and then I can call this the mode. And in fact, we even said before, when we have a distribution that has like 2 humps, 2 maxima, we call this modal. So we even already used that word mode. We have like kind of two contenders for the most frequently occurring data value. So these bimodal distributions, we already used the word mode. We already have seen this concept come up before. Now, unfortunately, this idea of bimodality hints at one of the big problems with the mode. So let's jump up here and grab our Ashley, Brandon, and salary data. And we say, okay, if the mode works fairly nicely on something as bad to work with, so to speak, as qualitative data, it should work just fine on numerical data, right? Well, so if I look at my Ashley data, 5, 7, 8, 9, 11, well, what's the mode? I mean, I just have 5 data points that have 5 different values. Is this like, is the, I called this bimodal, saying that it has 2 modes. Does this one have like 5 modes? Do we call this like 5 peaks? Uh, does it have no mode? Right? At what point do we go from saying, oh, we have 2 modes to saying we have no modes? It seems like if we have 1 mode and it's clear, that's good. If we have 2 modes that are clear, we say we're bimodal. But like if we have 3 modes, do we call it trimodal? If we have 10 modes, do we call it 10 modal? At what point do we just kind of call it a day and just say, okay, we're going to say there's no mode now? Or kind of even worse, if we had, let's say, a die roll that we know is in theory uniformly distributed, should have essentially no mode. But, if we roll a die 100 times, because 6 doesn't go into 100 evenly, we're going to just by chance most likely get one number that has just a little bit higher frequency than the others. So now this guy is the mode. But if I repeat this experiment, next time I'm going to probably get a different mode, and next time it's going to jump somewhere else. This is certainly not indicative of a typical data point, whether we're in the Ashley data or the die rolling data, or right. So the mode can have these kind of pitfalls, right? Kind of as kind of a rough way of thinking about it, if you have lots more uh, data points than you have bins. So one of the problems is that this Ashley data, I mean, if this is tax returns per day, let's say maybe we have 20 bins, like you could reasonably get between, I don't know, 0 and 19 tax returns done in a day. So we have like 20 bins, but we only have 5 data points, right? If I had 500 data points for 20 bins, well, maybe that would work a little better. So if I have a lot of data points relative to the bin size or the number of bins that I have, and also if I'm pretty confident that my underlying population isn't like uniformly distributed, but kind of actually has some kind of peak, like maybe a bell curve or something like that, or even it could even be skewed. But if I'm reasonably confident that my kind of underlying population has a peak, and I have a lot of data points relative to the number of bins, then my mode's probably okay. But that's a whole lot of caveats to use the mode when we have some pretty darn good measures of center already. So the mode, again, really saves the day in things like qualitative data, because that's pretty much the only thing we can do is just count the number in each bin and then use that count to somehow make an ordering of some sort. But there are some downfalls with mode. And in fact, if we come over to our Excel sheet, and if we try to compute the mode for, say, the Ashley data, equals mode. Oh, and it even got smarter. See, Excel's gotten smarter. Mode multiple or mode single. We'll use the deprecated function, just mode. Well, it doesn't like this at all, right? If I calculated the mode of the salary data, well, here it does actually come up with a mode of 28. Do I think that this mode is meaningful as a measure of center? Yeah, maybe or maybe not, right? Because I mean, in salaries, maybe there's just a few people who we sampled who do the same job and get paid the same salary because that job gets paid that salary. Maybe that is indicative of that being the typical person, right? If we're at a call center or something and like everybody who does this job gets paid this salary and like there's a whole bunch of people that do that job and that's why we got 3/7 of our sample was this number. Maybe that is something like a typical data point. Um, but it's a little hard to tell on such a small sample. So I think kind of as a you know kind of rule of thumb, um, maybe try to stay away from the mode unless you're in something like qualitative or categorical data. That might be a place where it's really well used. It's also used a lot in mathematical statistics because of this idea of we often want to find the maximum value of these curves, but that's not something we're really going to get into in this course. But again, we have situations like this where where almost everybody would say there's no mode. We have situations like this where there might be a clear mode, 3/28, most frequently occurring data value. If we were to group data, if we had a range like this and we decided to group into bins of size 10,000 or something, if we had a larger number of data, we might have a different perspective on the mode if we choose to group our bins in different ways. Okay, so I think that is all I have to say about the mode. Any questions on that? All right, and then the last big idea in this section, the weighted mean. I'm going to post a supplement. It's actually already up, but I'll just point you to the YouTube video for geometric mean and harmonic mean. So I have a recording for that that um, we'll just defer to for those two. They're both kind of tangential topics, but I think it is good to kind of see where they fit in, especially for geometric mean. It does pop up quite a bit in some fields. So the idea of weighted mean is actually a quite important one, and it's one that you've probably encountered before, but maybe not, had a name for it. So let's look at an example here where we have a final grade calculation, final course grade calculation. In the syllabus for some course, this isn't our course, so don't get worried if you're like, wait, I didn't take any quizzes. This isn't, for our course, this is just an example. Maybe there were 4 assessment types: homework, quizzes, midterm exam, and final exam, and they had different weights. Homework was weighted at 30%, quizzes 10%, midterm exam 20%, final exam 40%. Pretty typical, right? It's pretty typical that different assessment types in a course are weighted differently. Quizzes are a little lower value, a little lower risk, so you can use those more for just kind of self-assessment. Final exam, well, you really should have your stuff down by that point, right? You really want to put a lot of work and effort into that, for instance. Now, suppose you got these scores on each of these at the end of the semester. Your homework average was 90%, your quiz average was 50%, midterm exam average, or one midterm exam score 75%, final exam score 80. And the question is, what is your final course grade? Well, what we want to do is we want to do a weighted mean. I want to average together these scores, but not just like a 90 plus 50 plus 75 plus 80 all over 4. I want to average them relative to these weights so that this final exam score of 80% gets weighted pretty heavily, but the quiz score of 50% gets weighted much lighter. So what is our formula for the weighted mean? So suppose we have data x1 through xn. These would be like your scores. And each data point has an associated weight to it. W1 through Wn. And we'll assume these weights are positive. You probably could get away with having negative weights as long as you do things like not divide by 0 and so on, but we'll assume the weights are positive. It's probably the most sensible thing. I had one of my teachers in undergrad would often say is like, yeah, I want to make the Maxwell SAT. There was some SAT scoring system where they like took like math plus twice verbal, and that was like important for people. Like they basically doubled the impact of the verbal score on the math. I don't know. They've changed the way that they've evaluated it many times over the years. Because like I want to make the Maxwell weighting where it's like 10 times math minus 5 times verbal or something like. So I mean, I suppose you could do negative weights if you wanted to. Like it probably wouldn't hurt anything, but would be kind of hard to interpret. So we'll assume these weights are bigger than 0, but we actually don't have to assume anything else about them. We often choose weights that add to 100% or that add to 1, and we'll see why that makes things a little bit nicer as far as the calculation goes. We'll see that in a minute, but really these weights only need to be positive. I suppose it wouldn't hurt to have a weight of 0, but if you're going to weight something at 0, then, why even worry about it? Okay, so what is our weighted average? Well, what I want to do is I want to multiply my data points by my weights. So I have x1 times w1 plus x2 times w2, and so on through xn times wn. But I want this to be an average. I could have picked huge numbers for my weights. I could have picked, weight 1 to be 1,000 and weight 2 to be 10,000 and weight 3 to be 3,000. Or I could have picked weight 1 to be 0.1, 10%, weight 2 to be 1.0, weight 3 to be 0.3. I think I got all those ratios, right? So I don't want my answer to be dependent on the size of the weights. I want it to be dependent on the relative values of the weights. How does weight 1 compare to weight 2 compare to weight 3? So I want to divide out the scale of my weights. Or I want to divide by the sum of the weights, W1 through Wn added together. Now, a little side note, if all of my weights are 1, if Wi is identically 1, this kind of triple equal sign means it's identically or always equal to 1, then the weighted average is just the mean, right? Because I just have x1 times 1 plus x2 times 1 and so on plus xn times 1. The numerator is just x1 through xn added together, and the denominator is just 1 added to itself n times. That's just n. That's just x bar. And in fact, if my weights are all equal to one another, even if they're not equal to 1. So if all my wi's are equal to all my wj's, let's just say that it's w, then I just have x1 times w plus x2 times w and so on. And then I just have a whole bunch of w's on the bottom. Well, my denominator is just n times w, and my numerator, I can factor out a w. I just also get just the mean. So if my weights are all the same, if they're all 1, it's obvious I get the mean just by plugging in. But even if they're all the same and not equal to 1, if they were all 10 or something, I still get just the mean. So the scale of the weights is not important. It's their relative magnitude. How big is weight 1 compared to weight 2 compared to weight 3? So another side note is if I choose weights, if I choose to scale them myself ahead of time, such that they add to 1, if I choose weights such that they add to 1, my denominator ends up being just 1 and can effectively be ignored in this context. We have to be very careful about this, though. It might be tempting to do this and then to generalize this and say, oh, I can just always ignore the denominator. Well, that's not the case, right? If we didn't have weights that added to 1 or 100%, then this denominator would have an impact. But in the case that we do have weights that add to 100%, we can ignore the denominator. Okay, so these are my W's, like W1, W2, W3, and W4. And these are my data, X1, X2, X3, and X4. So let me actually come up here, just erase this. So then what is my weighted average? What's my final course grade? Well, 30%, 0.3 times 90 plus 0.1 times 50 plus 0.2 times 75, and then 0.4 times 80. Now this is all divided by 0.3 plus 0.1 plus 0.2 plus 0.4. I do note that this denominator does end up being 1, so I can ignore it, but that's always a good thing to just check on in each case, because the denominators don't always add up to 1. Okay, so I need 0.3 times 90 plus 0.1 times 50, 0.2 times 75, and 0.4 times 80. I think that all looks good. And that gives me 79 as the weighted average. So the average rate 79, just barely shy of a B. Another question we might be interested in as students that, comes up often is, I'm part of the way through the class. How am I doing up to this point? So what is like a mid-term grade? Well, what might it look like when I'm at midterm grading time? Well, I won't have a final exam score, right? This is like question. Haven't taken the final exam yet at midterm grade time. Let's just say in this course that we have taken the midterm exam at that point. Note that the midterm exam is different than the midterm course grade. Those are two different things. The midterm exam there's typically one exam in the middle of a course and then one at the end. That's at least one of the ways to structure a course. And the midterm exam is just the exam in the middle of the term. And the midterm course grade is the course grade that's given in the middle of the term. So that's just why they're both called midterm. the quizzes that I have here probably only represent half-ish of the quizzes that I'm going to take throughout the course. The midterm exam is kind of set in stone. It is what it is. That grade's not going to change. But my quiz and homework grade, I probably have only completed half or so of that material. So it does kind of irk me a little bit that they ask me to give you a letter grade, A, B, C, D, F for a midterm grade. I would much rather it be like pass fail. I think that's a much better, a much more accurate representation of what I'm trying to convey to you. But I have to enter a midterm course grade for you. So how do I calculate that? Now, it should be said that this is not a well-posed problem, how to calculate a midterm grade, or to say at this point in the course, what is your estimate of my grade? There are a lot of ways it could be estimated. We could say, well, take the midterm exam as a proxy for the performance on the final, estimate your final exam score by your midterm exam score. That would probably be a reasonable thing to do in a lot of cases. Where implicitly, if we're just using the homework and quiz grades flat out, your average in the first half, we're implicitly using your performance in the first half of, say, the homework and quizzes as proxies for your performance in the second half. That may or may not be a good thing to do, right? If the material in one half or the other is much more challenging for students, that might not be such a good idea. I could try to do something more complicated, like intentionally underweight homework and quizzes because these don't represent all of your homework and quizzes, but keep the weighting for midterm exam the same because this does represent fully your midterm exam score for the semester. It's quite complicated to tear apart what it means to give a midterm grade. But I'll tell you how I would do it. And I would do it this way basically because it's probably not too far off base from, it's probably not too different from any of the other ways of computing it. And it's easy to understand. So, when you look at a midterm grade, if you see that your midterm grade is B, like don't be super surprised if you end up with an A or a C if you work similarly through the rest of the course. But you should be surprised if you work similar through the rest of the course and ended up with an F, right? That's really the kind of coarseness that we're dealing with here. If you expect an ABC and you get a midterm grade that's somewhere in the ABC range, that's probably concordant. If you're expecting an A and you see an F, or if you're expecting an F and see an A, something's probably quite a bit different than what you were expecting. So how would I compute this? Well, I would say, okay, we don't have any explicit final exam data, so let's just forget about final exam altogether. So I would take these 3 data points, and I would just use the homework and quizzes as they are, whatever the average is at the time that the computation is done, along with these 3 weights. Now, something to note is that these 3 weights don't add up to 100% anymore. They add up to 60% now because we've ignored the final exam contribution because we don't have that data yet. So what's my new weighted average, my midterm grade weighted average? What's going to be 0.3 times 90 plus 0.1 times 50 plus 0.2 times 75 divided by the sum of my weights, 0.3 plus 0.1 plus 0.2. Little calculator trick, if you do second enter, it brings up the thing you just typed in. If you do second enter again, it'll bring up the thing you typed in before that, and so on. So I want to delete the stuff after the 0.2 times 75, but I want to keep the rest of the numerator. Gives me 47, and then I divide by 0.6. And that gives me 78.3 or so. So if I scored an 80 on the final exam, that's about in line with what my midterm, quote, midterm grade was. And my weighted average didn't change much because I added a new data point that was kind of in line with the quote typical data point already. If I had scored much higher on my final exam, I'd expect the 78.3 or so to have gone up quite a bit. Or if I scored a lot lower than 78, 80, something like that on the final exam, I'd expect my 78.3 to have gone down quite a bit. So you can compute weighted averages on incomplete data, and this is probably the way that I would lean towards doing it. Again, there can be an argument made for like, should we change the weights for homework and quizzes if we've only completed about half of them to like 15% and 5% and weigh those against the 20% for the midterm exam? Maybe. Um, these are, this is an important thing in statistics that even though this calculation is a hard calculation, right? It's like a hard in the sense that everybody should get the same answer. There should be no debate about what the answer is. Once we make the choice of how to compute, of what weights to use and what data to use, the question of what weights should I use, what data should I use, should I take the midterm exam as an estimate of the final exam and just basically copy that 75 down again? Should I adjust the weights of the homeworks and quizzes because we only have like maybe half-ish of them completed, where we've completed all of the midterm exam? It's just one point in time, we complete it, it's done. Should I use that full weight of 20% versus say a 15 and 5% weight for the homework and quizzes because they only represent half of all the homeworks and quizzes? Those are all debates that have to be had before we do the calculation. And those are decisions that we have to make, and those decisions will influence the result. So this is another thing that people, some people don't really like so much about stats, is that there are so many of these types of decisions that need to be made on the front end. And sometimes it's not super clear, right? How to make them. And we had discussed that a little bit already. Like, how do should I report the mean or the median? If I just want to report a measure of center, if I want to report the average salary, should that be a mean or median, or an average tax returns per day, mean or median? Those would both be good candidates. When should I use one versus the other? Okay, so any questions on any of that? All right, and then just a really little aside, kind of a tangent, um, on the relationship between the different measures of center. So um, we could go quite a bit into this, but it's beyond the scope of this course, so I'm not going to. But if we look at these measures of center, it kind of seems like we just have this. Let me scroll back up to here where they're all listed. Seems like we just have this motley kind of random assortment of different ways to answer the same question. And it seems like they just, one person decides to do it this way and they make the mean, and another person created the median, another person created the mode or the weighted mean. And like, they don't really seem to be linked together too well. Maybe we saw like how the weighted mean was related to the mean, but I think for the other ones, it's kind of hard to see. It turns out that these are really all just variations of answers to the same mathematical structure, the same mathematical question. These all really derive from the same mathematics. And on the surface level, they look very different from one another. But if you go a step or two deeper, they're really all kind of the same thing. So what is the mean? If I create a function that the mean of some data, let's say x1 through xn, if I create a loss function, which I might just call, whatever, L of little x or something like that. So I want to build the mean from first principles. I have data, x1 through xn, and I have this mean that I'm going to call m, this number that I'm going to call m that relates to the data x1 through xn. And if I'm looking for the typical data value, if I want m to represent a typical data point, well, I would think that it would be nice if m was kind of close to a bunch of the data points. So I want to look at things like x minus m. If this difference tends to be kind of large in absolute value, then that choice of how to compute m might not be a good thing to call a mean, because if this m, this way that I compute m, tends to be far away from most of the data points, it's hard to argue that it's a typical data value. On the other hand, if this difference tends to be small, m tends to be close to a lot of the data values, then maybe we can say that it answers this question. For the mean in particular, I'm going to look at a loss function of x minus m squared. And then what I'm going to do is I'm going to add up. I'm going to look at some function that's adding up L of xi. So it's adding up xi minus m squared. And this is kind of like an error in a sense. Like, in a sense, kind of the perfect setup would be if my data set consisted of data points that all had exactly the same value, then my typical data point is a very clear answer. It's just that common value. My measure of center should just be that common value as well. And that would make all of the components of this sum equal to 0, right? Because the difference, the deviation from the supposed mean and each of my data points is going to be 0. So if I add up 0 squared a bunch of times, I get 0. In reality, I have data sets that have lots of different data values. So if I'm just picking one number to represent lots of different numbers, there's always going to be some error. But I would like to choose m so that I minimize this function. And the way that I choose m is the average. So if I plug x bar in for m here, that always minimizes this kind of like sum of squared deviations. We have deviations between m, the mean, and each of the data points. We square them, and then we add them together. We'd like to minimize that. And the minimizer, the choice for m, for the measure of center that minimizes that, is x bar. So for this kind of quadratic loss function, that's related to x bar. If my loss function was, instead of being quadratic like this, if it was, say, an absolute value, like absolute value of x minus m, just the linear distance away, the relationship is with the median. The median is the minimizer of that. So this is actually pretty easy to show, the one with the mean. If you have a little bit of knowledge of like quadratic functions from intermediate algebra, that's all you really need to solve this. The median's a little bit more nuanced to solve. If my loss function is the maximum of the deviation between the supposed measure of center and a data value. So I go through and I look at the deviation between the measure of center that I'm proposing and each of the data values, and I take the biggest deviation, really the biggest absolute deviation, I suppose. Then this relates to the mid-range. So the mid-range minimizes the maximum deviation. What else? If I'm dealing with the logarithm of data, so log data, that relates to the harmonic mean, or sorry, the geometric mean. Just thinking ahead. And if I'm dealing with 1 over data, that relates to the harmonic mean. So two means that we haven't seen that are going to be in the supplemental video. And if I wanted to do, so the mode is kind of, if my loss function looked a little bit like stuff to the 0 power, the math here is a little bit complicated and nuanced, but if instead of having like the second power or the first power, a maximum is kind of like an infinity power in some loose sense. If I had like a 0 power here, it's a little unclear because sometimes you get a 0 to the 0 power, and really the interesting bit is what happens when you get a 0 to the 0 power. But that is what the mode comes from. So it all comes from this structure of trying to minimize the sum of some loss function. If we choose different loss functions, we get different measures of center out. And if our loss function had a weight in it, if it was like, wi times this, that's where we get weighted mean over here. So it's the same mathematical structure giving rise to all of these seemingly very different measures of center. It's just a question of which so-called loss function do we choose as the one that we think is most appropriate to the situation that we're looking at. So it's not just like picking random tools out of a toolbox. It's like you have a bunch of different wrenches. They're all wrenches, but they're different sizes, right? If I use the wrong size wrench on the wrong bolt, it's going to strip it or it's not going to fit. So I pick the size wrench and the type of wrench that fits the bolt that I'm trying to unscrew. Similar kind of idea here, right? It's just a question of which loss function do I choose that gives rise to the measure of center. Again, this is beyond the scope of this course, but I think it is important because in math, a lot of times we introduce the surface level ideas, but that's not really, in my mind, where the mathematics lies. The mathematics lies in the deeper truths, the things that connect seemingly disparate things together. And this is where that connection is. It's not just that we have invented a whole bunch of random tools to use in different random situations and pick randomly from. It's that there's a deep structure here that gives rise to each of these. It's the same structure that gives rise to them all. But it's just a question of which, one little step in that structure, which choice do you make for this loss function? A very common one is to use the square and to get the mean out. There are some really good reasons for that and some, reasons like we use it because it's what everybody uses kind of reasons. So very practical reasons as well. Okay. Yeah, I think the last thing that I want to show really quickly is just how to do a weighted mean in Excel. And then we will wrap up section 1 and move on to section 2. So any questions before we look at this over here? Okay, so I have a set of weights and a set of grades. And I can go through and do this the long way. There's nothing really wrong with that. I can do, well, I probably want a parentheses. I can do this grade times this weight plus this grade times this weight plus this times this plus this times this. And n parentheses, that's my whole numerator. That's the numerator from over here. Oops, didn't mean to pick that up. That's this whole numerator. And then I need to divide by the sum of the weights, which I'll just do this way. The sum of those 4 weights. And I get my 79%. If I delete my final exam grade, well, you see that Excel isn't quite smart enough to adjust for that. So we also have to delete the weight. And we see our 78.3% here. There is a quicker Excel function we can do some product, and it asks for two arrays. So I can just input the grades array, the grades list, comma, the weights list. They have to be the same length so that it knows how to match them up. And we see we get the same answer. We do see that with some product, it can sometimes be a little bit glitchy. It can sometimes work a little bit outside the specs that we might expect, right? Because it's kind of expecting to do something with this last bit here. So I suppose we probably could adjust these. Let's see if that works. It still doesn't like that. Why doesn't it like that? Oh, brain fart moment. It's because I did not. So some product only does the product. I did not divide by the weights sum. So there we go. So that should work a little better. There we go. Some of these functions like average and median and so on can work a little bit differently depending on what you're doing when you have empty cells. So I thought that's what was happening there, but I'm going to chalk it up to still getting over this crazy cold. But we can use the sum product function as well. Makes it a little bit quicker. But I think if you only have a few cells, it's not too bad to go in and just type the thing in manually. And if you do it this way, you probably won't forget to divide by the sum like I forgot to do earlier. Okay, so any questions on 3.1 before we move on? Okay, let's start into 3.2 then. We should get an okay start on 3.2, but we'll save the big stuff, variance and standard deviation for next time. So again, we have our same two data sets or same three data sets that we'll deal with through this section as well. And our first measure of center is range, but we also have variance, standard deviation, and the coefficient of variation. So those are our measures of variation that we're going to look at in this course. And measures of variation. Measures of variation, try to answer the question, something like how variable, how spread out, something like that is the data set. So that's what we're trying to answer here. Just give me 1 second real quick. Okay, so yeah, measure the variation, trying to answer something like how variable is the data set, how spread out is the data, kind of how extreme can things get. So where measures of center, we're looking for the typical data point, kind of where's the middle of the data set, roughly speaking. Measures of variation are looking at how spread out is the data set. Our first measure of variation is pretty simple to compute, pretty simple to understand. It's called the range. Now, importantly, each of these measures is a single number. So we might see the word range and we might be tempted to report, say, two numbers, like, say, here, we might be tempted to report 25 to 100 or something as the range. But we want to give one number. We want to give a single number numerical description of the data set. So the range is the difference between the max and the min data value. So it's x max minus x min, or presuming we've ordered our data, it's xn minus x1. So we can see it's really easy to compute. We just have to be able to figure out the max and min data values. So we have what, 5, 7, 8, 9, 11 here. Maybe I will just put Ashley's data in order. And same with Brandon. We have 3, 5, 7, 11, 14. And we can see right away that the range for Ashley, it's not 5 to 11 or something like that. It's 11 minus 5 is 6. We also notice that we're just taking the difference of original data values. They come with units. The difference of two numbers that have the same unit is that original unit. So Ashley's range is 6 returns per day. In other words, if I were to look at a real line, she has one day that was a 5, 7, 8, 9, 11. Her data covers a swath of the real line that is 6 units wide. What's the range for Brandon? Well, 14 minus 3. Again, it's not like 3 to 14 or like the interval from 3 to 14 or something like that. It's 14 minus 3 is 11 returns per day. Brandon's data is come down a little more, go up a little more. Brandon's data is 3, 5, 7, 11, and 14. Brandon's data covers a swath of the real line that is 11 units wide, as opposed to 6 for Ashley. So it looks like Brandon's data, at least at a glance, is more variable than Ashley's data. Right? There are more extreme things that can happen in Brandon's performance than in Ashley's performance. Ashley's a little more consistent. Brandon's much more variable, it seems. And it looks like something similar with the salary data here. We have 25, 328s, 30, 55, and 100. So the range for the salary data, again, it's not like 25 to 100, it's 100 minus 25 or 75. Now we do want to remember that the salary data is in thousands of dollars. It's in a different unit than the Ashley and Brandon data. It's also just a very different thing that we're talking about, returns per day versus salary. So we wouldn't want to look at this and say like, oh, the salary data is much more variable than the Brandon data. We'd be comparing different units. We'd be, right, we have completely different contexts. So we want to be careful about comparing, say, like salary against Ashley or Brandon, probably not a great idea. But comparing Ashley and Brandon to one another, same units, same context. They're both, like working in, say, the same tax firm or something. So maybe a little more reasonable to compare Ashley and Brandon to one another based on their variability and maybe not the salary data. So any questions on that? So one important note is that the range is a measure of variation, and it's the difference between the extremes. It's easy to get that confused with the mid-range, which is a measure of center, and it's the average of the extremes. Right? They have the word range in them because they both kind of deal with just the extremes, but the mid-range, it starts with an M, so it's one of the measures of center like mean, median, mode, mid-range. That's an easy way to remember it. It's a measure of center, and it's the average of the extremes. So if you take the two extremes, it's kind of the midpoint of them, where the range is the difference between the extremes. It's the amount of space in between them. So if you take a wider swath, you have a wider range. Both of them just deal with X max and X min, but we just have to be careful which one is a measure of center, measure of variation, and how they're computed. So it's a little easy to get them mixed up, but I think with the M trick, mean, median, mode, and mid range, kind of all go together. That helps a little bit. Now, one of the downsides of the range, and also the mid range for that matter, but one of the downsides of the range is, well, it only looks at two data points out of the whole data set. Right? If I was looking at, say, the variability of grades in a class, well, let's think of this from the standpoint of measure the center, right? If we look at measure the center first, if I imagine a class that has, say an average score of 80% on an exam, and another class has the same average score of 80% on an exam, but the first class, every single student in that class got an 80%. Nobody got an 81 or a 79 or anything else. In the second class, half the students got 60 and half got 100. Well, clearly that second class, I mean, the averages are the same, but the second class is much more variable. It has a much bigger range, right? Say 10 students got 60, 10 students got 100, still averages to 80. The first class, everybody got 80. Of course, averages to 80, but the range for the first class is like 0. It's like 80 minus 80. Like there's no variation at all. Everybody got exactly the same score. The second class, 100 minus 60, there's a 40-point range. It's kind of like a coin flip, whether if you pick a random student, they got a bad grade or a good grade, where in the first class, everybody got the same grade. There's no variation at all. But we can maybe imagine a third class where like almost all the students got exactly 80, but one student got a 60 and one got 100. The average would still be 80, but the range is now 40. How do I tell the difference between the class where like half the students got 60 and half got 100 and the class where like one student got 60, one student got 100, and everybody else was in the middle? That one's much less variable, right? If I pick a random student, I'm probably going to get somebody that got 80. Probably not a really low or really high grade. There should be less variation in, so in a class that looks like this, we should call that less variable than a class that looks like this, where everybody is kind of, split. Well, oops, that's not a straight line, where everybody is split way away from the mean. This seems much more variable than this one. There's just kind of a couple outliers over here, and over here, it's like we have complete bimodality. But these would have the same range, right? These cover the same swath of the real line between the extremes. So the range has this downside. It only looks at two data points out of the entire data set. There could be a data set of size 1,000,000, and it's only going to look at two data points to determine the measure of variation. So it's quick, it's easy to do, it's easy to understand, but it only looks at two data points out of the entire data set. How can we construct something that has maybe kind of a similar feel, that when I have data points that are further away from kind of the middle of the data set, my measure of variation goes up? How can I do that while looking at all of the data points? can I touch every data point and allow each data point to have a contribution so that I can distinguish between two situations like these? And that's kind of the goal for next time, is to develop the variance and the closely related standard deviation kind of from first principles, and then go through some calculation examples for those. All right, I'm going to stop the recording.